This video is going to be the video for what we're going to cover in class on Tuesday the 12th for those that are missing class for either AP exams or absence. So this was the warm-up they had to do. Go ahead and pause it and see if you can find out the solution. So to expand the quantity x plus 3 quantity cubed, obviously we're multiplying x plus 3 multiplied by itself 3 times. The easiest way to do that obviously is to multiply one of the quantities, so it's a special case, perfect square trinomial there. So you end up with x plus 3 times the quantity x squared plus 6x plus 9, and of course multiplying out you end up with combining like terms and getting x cubed plus 3x squared plus 3x plus 27. So a lot of work doing it by hand. One of the things we're going to talk about in this lesson is how to quickly do this without having to do all that long multiplication. In order to do that, we need to talk about the answers to our question for number 2, which is what we looked at yesterday in class. So 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. Should get the answers of 1, 3, 3, and 1. So today's lesson is going to talk about the binomial theorem, and the homework that's going to be assigned is page 717, numbers 2 through 16 even, 22, 24, and 35 through 38 all. We're going to wait to go over the answers to the section homework from 9.1 tomorrow so that we can answer everyone's questions all at once, and then that way you can work on these questions as well on Wednesday. So Pascal's triangle, think way back. You've probably talked about Pascal's triangle before. You know it looks like this. On the outside it's surrounded by 1s, and then there's all these other values that talk about that you fill in, and of course if you remember the pattern, you basically take the 2 above it and add them together. So for example, 1 plus 1 gives us 2, or 5 plus 10 gives us 15. So that was the pattern that you used to fill in Pascal's triangle. And again, we started with 1s on the outside here. But believe it or not, Pascal's triangle has a lot of different applications, and one in particular goes with our combination stuff that we did yesterday. So this idea of this n choose r that we talked about yesterday, the n combination r, we can actually find these values on Pascal's triangle very easily. What we need to keep in mind is that n, in this case, is the row. Now, because we're doing our Pascal's triangle always starting with 1s, we're going to say that the first row, we're going to call it row 0, because it really doesn't have a value that's new in it, just start with the 1. And so in the same respect, we're going to look across and we're going to talk about the cells. And we're also going to start at cell 0. And again, this is all due to the fact that we're starting with a value of 1. So for example, this would be row 0, row 1, etc., row 2. So this would be cell 0, cell 1, and cell 2, and so forth. So when I'm looking at this Pascal's triangle, I can quickly find the answer for 8, choose 3, just by looking at row 8 and cell 3. So if I count down, again, starting at row 0, and go down to row 8, and over to cell 3, we find that the value is 56. And again, if you plug in your calculator 8, choose 3, you should find the value is 56. It's a nice way to kind of quickly find the value without having to calculate it, of course, if you have Pascal's triangle. Now, obviously, we want to think about what this would be in terms of how do we use this in terms of expanding. So how can we use Pascal's triangle to help us expanding problems like this, where we've got the quantity of x plus y squared? Well, if I wanted to multiply x plus y times x plus y, I'd found out the answer is x squared plus 2xy plus y squared. Well, how can the Pascal's triangle help me? Well, if we look at the second row here, we see that the coefficients are 1, 2, 1, which when we multiply out x plus y quantity squared, we get these leading coefficients of 1, 2, and 1. Could we do the same thing here? Let's multiply out the quantity x plus y to the 5th. This is not something we want to easily do by hand. We saw how long it took us to do the warm-up when we had x plus y quantity cubed. But if I looked at the 5th row of Pascal's triangle, I can see the leading coefficients are going to be 1, 5, 10, 10, 5, and 1. And all I need to do to figure out the variables that go with it is I know that when I multiply this out, the first term is going to be x to the 5th, and the last term is going to be y to the 5th. And all the values, when we have combinations of x and y together, we start with our largest power of x first, and our largest power of x be x to the 5th, and our smallest power of y, which is technically y to the 0. X to the 5th times y to the 0 is just x to the 5th. So basically what we're going to do is start with our x highest power and go down along the way, and start with our lowest y power and go up along the way, giving us an answer of x to the 5th 5x to the 4th y plus 10x to the 3rd y squared plus 10x squared y to the 3rd plus 5xy to the 4th plus y to the 5th. This is much faster and easier than actually multiplying it out by hand. Well, let's just say I want to find one term of the expansion without actually having to multiply it all out. So let's say, for example, I wanted to find the fifth term of the quantity x plus y to the seventh power. Well, we know which row we need to look at on Pascal's triangle. It's going to be the seventh row. And of course, we know to find the fifth term, we would count 0, 1, 2, 3, 4, all the way up to 5, and find that our value is going to be here 35. Remember, when we were counting across, we wanted to find the fifth term, which in this case was the fourth cell, because remember we start with counting at 0. So I really found 7 choose 4 to find the leading coefficient of this term as 35. This will help us when we don't have Pascal's triangle in front of us, or we have a value that's too large to draw out Pascal's triangle. So we know how to figure out the coefficient, but how do I find the xy variable that goes with it? Well, we know it's going to be x cubed y to the fourth, but how do we know that? Well, if you think about the pattern of what happened, we think about the exponent that we started with. When I do my leading coefficient, I find that my x variable is going to be the same value as whatever the n minus r is. So 7 minus 4 gave us our 3. And then our r value was what our coefficient or exponent for our y value was going to be, which was 4. The one thing we know is that these two, the x variable's exponent and the y variable's exponent, must always sum to my exponent up here that I'm adding up to. Because we know at the highest power is 7, so our x and y terms have to, in this case the exponents, have to add to be 7. Let's try one more. Let's say we want to find the 8th term of the quantity x plus y to the 13th. Again, I've given you one that you can't look at Pascal's triangle. We need to think about the pattern. Well, how do we find the leading coefficient of the 8th term? Well, we know it's going to be in the 13th row. So to find that value, we're going to do 13 choose 7. Again, remember the 8th term, we'd have to go starting at 0 over to the 8th term, so that would be counting over to 7. So plugging that into our calculator, 13 choose 7 gives us the leading coefficient of 1,716. Now, what's our coefficients? We got our coefficient, we need to figure out our x and y terms. Remember, how do we find the exponents of the variables? Well, we know that the y term is going to be the same as the r, so that's going to be the 7th. And since we know that our n minus r and r have to sum up to n, that means that our x variable would have to be the 6th power. So here's what we were just saying here. So it's going to be x to the n minus r power times y to the r power, giving us an answer of 1,716 x to the 6th, y to the 7th. What I'm most likely going to give you when I have a problem to the 13th power is something like this. I'm not going to ask you to expand x plus y to the 13th power. Although you could do it, it's a little crazy. And you can see why when we start adding coefficients into the x and y, this becomes a little bit more difficult. But let's look at a couple. This idea of the binomial theorem takes what we just did and put it into practice. When we talk about this idea of this combination, another notation that you'll see written instead of saying n choose r or n c r is you'll see something that looks like this. N is still going to be the top number here, but r is this value that's going to be on the bottom. So it's kind of written like a fraction without the fraction bar. This is the same thing as saying n choose 0, n choose 1, and so forth. And remember, we have our formula to figure out these values of n choose r. And again, the pattern holds true. We start with our highest exponent of our first variable and end all the way with our largest exponent of our second variable. You don't need to memorize this or write this down. This is just explaining the process that we've just done, the binomial theorem. Let's look at this in an example when we don't just have variables, we have a constant. Let's think about our warm-up example that we had. How could we expand this using binomial theorem without having to multiply out the quantity x plus 3 cubed? Well, what we know is that the leading coefficient in front of these is going to be based on the combinations. So 3 choose 0 is going to be our first term's coefficient, 3 choose 1, then 3 choose 2, then 3 choose 3. Binomial theorem says we start with the highest exponent of the first term and the lowest exponent of the second term. So that's why we have x to the third, 3 to the 0. I know this value is going to be 1, but I find it helpful for students to see that these two exponents are always going to have to sum to the exponent I have up here. I apologize for the fact that these are both 3's. Know that this 3 determines where this 3 is coming from, and this 3 determines where the top value and our choose values are coming from. So our second term would be 3 choose 1, x to the second, 3 to the first. Again, these two exponents add to 3. Then our third term would be 3 choose 2, x to the first, 3 to the second. Again, notice the pattern. Our first variable's exponent is decreasing, while our second variable's exponent is increasing, till finally we get to the very last term, which is 3 choose 3, x to the 0, 3 to the third power. Remember from Pascal's triangle that we know that any number choose 0 and any number choose itself will be 1, because in Pascal's triangle we always start and end each one with a 1. So plugging in the values we have, 3 choose 0 is 1, x to the third is x to the third, 3 to the 0 obviously is going to be 1. 3 choose 1 is going to be 3, x squared is going to be x squared, 3 to the first, can't do anything with that. And of course we can go ahead and multiply out, and we end up with our first term being 1x cubed plus 3x squared times 3 plus 3x to the first times 9 plus 1 times 27. Again, all I've done so far is simplified. This 3 to the 0 became 1, this 3 to the first became 3, 3 to the second became 9, and so forth. Notice that I still have some coefficients I need to multiply, like this one here, so we're not quite finished yet. These two middle terms need a little bit more work, and multiplying out, we see our final answer is x cubed plus 9x squared plus 27x plus 27. This would be our final solution. It seems like there's a lot of work, and I don't expect you to show every single step here, but I think it's important to see how I got from the first step to the last step. And if it helps you to write them out, it actually is very helpful, particularly when you have a coefficient in both terms instead of just one term. It also is very helpful when you have a term that's not plus here, but minus, because we know that the sign changes based on whether the exponent is even or odd. Let's end this by doing one more example. Let's find out something where, again, the term switches in the middle, so it's x minus 4 quantity cubed. We know, again, the coefficients, because we're still looking at that third row. We know we've got 4 terms. We know the leading coefficient is going to be 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3, based on Pascal's triangle. We know we start with our highest exponent of our first term, and we start with our lowest exponent of our second term. Following the pattern, we can see why we're going to alternate terms. Negative 4 to the 0 is obviously going to become 1, but negative 4 to the first is going to be a negative. This second term is going to be negative. Then we've got a negative 4 to the second power, which is going to make this positive, so the third term is going to be positive. Finally, our last term, negative 4 to the third, is going to be negative, so this last term is going to be negative, which if you think about it makes sense. We should multiply out and alternate positive, negative, positive, negative. So multiplying out, again, I'm showing every step here. Finally, multiplying completely out, we end up with x cubed minus 12x squared plus 48x minus 64. Take some time and make sure you work through this and make sure that you got this answer. And this will be the types of problems that you're going to see.